now that we have all that out of the way, let me get started. Hello, everyone. My name is Shweta Ram. I am an applied scientist at Amazon, and today I'm excited to present our work, DreamBlend, advancing personalized fine-tuning of text-to-image diffusion models. This is joint work with Tal, Chianli, Andrew, Son, and Trishul from Amazon and Caltech. And this is based on our WACI 2025 paper, which is cited right here. Let me also get my laser pointer started. Okay, there we go. Okay, so by now, we are all familiar with text-to-image generation. Given a prompt like a photo of a teddy bear, models like Stable Diffusion can synthesize realistic images of whatever we asked for. Like, for example, here you see multiple teddy bears, and notice that each teddy bear is different, and each time we get a different teddy bear. But yeah, these are great. They can capture not just object identity, but style, context, and composition. And really, these models have transformed how we create visual content. And today, it's possible to generate high quality, photorealistic, or stylized imagery from just a few words. However, in many real world applications, this kind of generation is not enough. Users often want to generate images of a specific subject in diverse contexts. Now, let's take an example. Like here, I have a few images of my teddy bear. And instead of generating just any teddy bear, what I might want is this teddy bear in different contexts. Like maybe I want a blue house in the background, or I want my teddy sitting in a wheat field. So this problem is known as personalized text to image generation, where we are interested in one particular subject. Now, to do this well, we need to get a few things right. First is subject fidelity, which means the generated subject should look like my original. So I have a few images of Teddy here, and these are the generated images given this prompt, a Teddy with a blue house in the background. And we would expect that the Teddy in these images looks like the Teddy in these input images. So that's the first one, subject fidelity. Second, we have prompt fidelity. So this is the prompt, Teddy with blue house in the background, and we would expect adherence to this prompt, which means, well, we need a blue house in the background in this example. And finally, we would also like diversity. And what we mean here is that the outputs should vary across poses and settings. So in this example, the Teddy should be in varied poses and environments. It should have diverse elements like, let's say, the lawn here, a driveway, a few trees, and so on. So these are the three things that would be our success criteria for the problem of personalized text-to-image generation. Now, for very well-known entities like Barack Obama or Eiffel Tower, models can do this out of the box. So if you take Stable Diffusion and you give it a prompt like a photo of Barack Obama in front of the Eiffel Tower, this can work just through prompting. And the reason is these subjects were abundant in the model's training data. So as the model was being trained on like all of the internet, somewhere it saw Barack Obama and Eiffel Tower multiple times. And so it knows what these concepts are. On the other hand, for new or rare subjects like my teddy bear, prompt engineering alone cannot work. There is just too many things to describe, and it's pretty much impossible to get this to work with just prompting. And that is why methods like DreamBooth have emerged, which fine tune a pre trained model using just a few subject images. And we teach the model this new concept of my teddy bear post training. And once the model has learned this concept, it is able to use it in generations. So this problem combines few shot learning with the generative modeling aspect. All right. So now, given just a few subject images, we can fine tune a train text to image model to generate that subject in novel contexts, as we just discussed. So in this figure, we see again the few short examples of our subject Teddy. And over here, we see the classical DreamBooth fine-tuning steps. So you start with a pre-trained text-to-image model like Stable Diffusion, and then you start teaching it like my teddy as the text prompt. And for images, we use these teddy bear, and we train it for a few steps. And after that, we prompt it saying a photo of my teddy with a blue house in the background, and then it generates a few images. So now, as the fine-tuning steps progress, we can see what kind of images are generated. And here, we clearly see that there is a trade-off. These early checkpoints have high prompt fidelity and diversity, but they have very low subject fidelity. And this is understandable because we just started fine-tuning and we have not yet learned the subject very well. As we continue to fine-tune, the later checkpoints, they have very high subject fidelity. However, they have low prompt fidelity and diversity. Now, this happens because of overfitting and catastrophic forgetting, where the model starts associating all input latents to this subject. So, this is the trade-off in traditional DreamBooth fine-tuning. And our key contribution is to blend the strengths of underfitted and overfitted checkpoints. So we introduce DreamBlend. This is a method that merges the prompt fidelity and diversity from underfit checkpoints and the subject fidelity from overfit checkpoints during image generation. The generated images have layouts of the underfit images and the subject fidelity of the overfit images. So here in this column, you can see our result. So if we take the first image here, and the first row, first column image here, see that the layout of these two images is the same. And this teddy here has been replaced by our teddy. Same with this example where we have similar layout and the teddy is sitting in a similar pose. It's just replaced with our teddy. And finally here, we have an image of this teddy bear standing, and we got our teddy standing in similar layout. So basically, if you look at it, it looks like we took this image and we somehow replaced this subject with our subject. And in course of this presentation, I will go over how we are able to do that. And if you have played with this kind of DreamBooth and custom diffusion and these kind of personalized fine-tuning methods, you will notice that it's very difficult to get an image of a standing teddy bear like this. Like once you start fine-tuning, like all these images are sitting teddy bear, and it's really difficult to get this. The only reason we are able to do it is because we took a very underfit checkpoint where it is still possible to get these kind of images, and then uh, came up with a way to get this teddy to look like our teddy. Okay, so let's zoom into this personalized fine-tuning trade-off that we were talking about. So this figure shows images generated by different checkpoints for the prompt, a backpack on a cobblestone street. As a stable diffusion model is fine-tuned from 5 to 1000 steps. Again, we see the same trend. Early underfit checkpoints have higher prompt fidelity and diversity, but low subject fidelity. At step 5, the model respects the prompt, but this backpack doesn't look like our backpack, right? And finally, as we progress through fine tuning in later checkpoints, you can start seeing higher subject fidelity, but now there is lower prompt fidelity and diversity. Like these images start looking very similar to one another, and also there is no cobblestone street anymore. And if we continue this process, at step 1000, we see that the model starts to just output the input training images. Like whatever you give as the prompt, you will get one of these input images that was used for fine tuning. So this is the fine tuning trend, and existing methods will try to find a sweet spot through checkpoint selection. So basically generate these kinds of images and try to see which checkpoint looks good and makes a decent trade-off. So this is how they do it. And with DreamBlend, we are able to merge the strengths of the early and late checkpoints during inference. At this time, I can also mention that this is an inference time only method requiring small adjustments to existing techniques. Okay, so let's look at the attention maps. In text-to-image diffusion models, text conditioning is achieved through cross-attention layers, and these significantly influence the generated image layout. This has been well known now, and that is the motivation to look at the attention maps and try to understand what happens as the model starts overfitting. So this figure shows images generated at step 5, step 250, and step 1000 for our previous example. And we see the text-to-image cross-attention maps for different tokens. SKS represents this particular backpack. Then the rest are the words. So note that in all these cases, we started from the same initial latent. We use the same classifier free guidance, the same 50 steps of DDIM forward process, and of course, the same prompt. So except for the model's checkpoint, we keep everything else the same. At step 5, the model achieves high prompt fidelity. You can see backpack on the cobblestone street. And here diversity is not obvious because we have just one example, but if you generate a few, you'll see that the images are diverse. And if we look at these attention maps, SKS is focusing on this logo, and we have backpack, cobblestone street. They're all focusing on relevant parts of the image here. Now, if we go to step 250, we see that already the attention maps don't look as clean, and words like cobble are starting to focus on backpack, and same with street. You see some attention on the backpack here. And if we continue this process, by step 1000, the attention for all tokens starts to overly focus on our subject backpack. And this is a phenomenon that we have called catastrophic attention collapse. What we mean is that as fine-tuning continues, overfitting causes the attention of all text tokens to focus excessively on our subject backpack. So given this, now an intermediate model, like the one at step 250, still retains semantic understanding of concepts like cobblestone and street from its word knowledge, although their their appearances have started to morph closer to the concepts seen in the input images. So what do I mean by that? Like if you look at step 5 image, there is a bush here. And by the time we came to step 250, that bush was replaced by this tree bark. And there is a tree bark that looks like this in the backpack input images. So basically, the model is trying to replace everything in the image with something that it saw in the input images, because basically all concepts have started to look like something in the input images to it. Now, our key finding is that this model can be guided to generate an image that follows the layout of the image generated by the underfit checkpoint using cross-attention guidance. Here, CAG stands for cross-attention guidance. And we can see our result in this step 250 plus cross-attention guidance column, where we have the exact same layout, but this backpack has been replaced by our backpack. And the way we do that is with cross-attention guidance, where we try to get all these cross-attention maps to look like something close to this. So if we look at the second column here, the attention maps had started to drift away, but by enforcing these to look something similar to the step 5 image, we're able to generate this kind of an image. And by doing this, we are able to get both high prompt fidelity and high subject fidelity. By the time we go to step 1000, like we mentioned, we experience catastrophic attention collapse, and the model has started mapping all latents to one of the input images. At this point, cross-attention guidance is not effective, and we still get back the same image. However, an intermediate one like step 250 can be guided to generate this kind of the image. Here's the complete algorithm for what we do. So our input is the text features derived from our text prompt. We have a guidance model, which is actually our underfit model. And we have an edit model, which is our overfit model. And the output, of course, is the generated image. In the first step, we store the reference cross-attention maps when we generate an image using G. So just take the underfit model, give it the text prompt, and generate an image. And at each step of the diffusion process, we store the cross-attention maps in aref over here. So that is just the first step. And we also make a note of the initial latent that we started with. Then finally, in step 2, we synthesize the actual image using our edit model, which is our overfit model. This is where we do cross-attention guidance. So what we do is we start with the same initial latent, and at each step of this diffusion process, we enforce our current cross-attention maps to be close to our reference cross-attention maps for that time step. And then we have this R, which is our regularization loss, and alpha, which controls the amount of update. And we update our latent to encourage the current cross-attention map to be close to the reference. And we do this for all steps of the diffusion process. So that's the full algorithm with 2 steps. Now let's look at some of the results. So here in the first column, we have one of the input images just to see what the subject looks like. The second column is the overfit image. So if we used our edit model and directly generated an image, this is what it would look like. It is overfit and looks very close to our input subject, but hardly follows the prompt. The prompt, by the way, is right below here. So for the first example, it's a bowl on the beach. And then we have the underfit image. So this is the image generated by our guidance model. And finally, we have our result of starting with this underfit image as our reference image and performing cross-attention guidance using the overfit model. We get back this image. And as you can see in all the cases, the layout is very similar to the underfit image, and the subject looks very similar to what we see in the overfit model's image. So across various subjects and prompts, our approach successfully preserves layout of the reference underfit image as well as identity of the input subject. Here we have some qualitative comparisons with fine-tuning methods, DreamBooth and custom diffusion. So both these methods fine-tune the weights of the text-to-image diffusion model for personalization. But there's some difference about exactly how they do it. Now, we find that DreamBlend achieves a better trade-off in subject fidelity, prompt fidelity, and diversity compared to the baselines. So for example, if we look at the first one, backpack with the tree and autumn leaves in the background, both DreamBooth and custom diffusion are able to generate images for this. If we look closely, in the DreamBooth case, subject fidelity is higher, but the autumn leaves are not so obvious, the tree not so much. Here in custom diffusion, the subject fidelity is not very high, and in our result, it makes a better trade-off between the subject and prompt fidelity. Same way in the last example, a stuffed animal on top of pink fabric. So we see that DreamBooth and custom diffusion fail to generate the pink fabric in some cases, whereas in ours, it is able to do it because we started from a very underfit checkpoint where it was still able to generate these kind of images on challenging prompts. For completeness, we also compare to non-fine-tuning methods. Over here, textual inversion is an inversion-based method that learns an input word embedding to represent the subject. Clip diffusion and IP adapter are encoder-based methods offering zero-shot personalized generation. And finally, AnyDoor is a reference-based method that tackles the more challenging problem of placing a specific subject into a specified background image. So if we look at our results, find that compared to the fine-tuning based approaches like DreamBooth and custom diffusion and ours, which is based on those, uh, the subject fidelity and photorealism in these non-fine-tuning based methods is quite lacking, especially when it comes to more complex subjects like this backpack or the cat statue here. For the dog, a lot of these methods are able to do a decent job. And this is also well known that these kinds of methods are easy on cats and dogs and pets, those kind of subjects. But for like more complex subjects like this backpack here or this cat statue, it is very obvious that the uh, subject fidelity and photorealism is lacking in these non-fine-tuning based methods. Finally, we look at some numbers. This table shows metrics averaged over all subjects and prompts of this standard DreamBooth benchmark. And we can see our approach achieves the best Dino Clip Clip scores for both the SD 1.5 as well as the SD XL backbones. Uh, so here, Dino and ClipI, they are measuring the image similarity, and ClipT is measuring the text similarity. Now, in this figure, we visualize how DreamBlend advances the Pareto front for two example subjects. So we have the image alignment represented by Dino and text alignment represented by Clip T. And ideally, we would want to be as close to this top right corner as possible with high image and text similarity. And we see all operating points of methods, DreamBooth in black, uh, custom diffusion in red, and our method in green. And we see that compared to all densely sampled operating points of both DreamBooth and custom diffusion, DreamBlend achieves better trade-offs and it's able to access this part of the image text alignment space. Finally, we also did human preference studies comparing our approach to DreamBooth and custom diffusion baselines. Two studies were performed assessing overall preference and diversities for each baseline. So in the overall preference study, users choose between an image generated by our method and a baseline method for the same text prompt, considering both subject and prompt fidelity. And in the diversity study, users selected the more diverse collection of 4 images between our method and a baseline. And the results are in the table here. We see that for all 4 studies, our method is preferred over the baselines. Now, coming to the generalization, our approach is applicable to different fine-tuning methods like DreamBooth, custom diffusion, and LoRa, different text-to-image diffusion models that feature a cross-attention mechanism, as well as personalized editing of real images. For this, we used DDIM inversion. So from top to bottom, here we have Stable Diffusion XL fine-tuned with LoRa on the base, Stable Diffusion 1.4 fine-tuned with custom diffusion. This also shows multi-concept where we are fine-tuning for both dog and bowl at the same time to generate this result. And this is Stable Diffusion 1.5 fine-tuned with custom diffusion for one subject, candle. And finally, we have real image editing. So the personalized editing of a real image where we have this image and we want this cat to be replaced by our cat. Now let's look into the effect of this cross-attention guidance. Uh, so basically, an overfitted model, as we saw, tends to generate concepts that it originally saw in the input training images. So if we don't do anything, we will generate image like this with the image from, the woman from one of the input images. Now, by doing cross-attention guidance, we encourage it to follow the layout of this underfit image. And as a result, we by applying a small amount of guidance, we can get rid of the person. And then if we increase the guidance, we get back this city skyline. And that was the prompt, like we wanted a city in the background. Now, it is also interesting to see how this cross-attention guidance will play with the classifier guidance that is usually used in this kind of text-to-image generation. And for that, we have this grid here. Uh, Basically, increasing classifier-free guidance improves subject fidelity, while increasing cross-attention guidance increases the adherence to layout of the underfit image. And here's how the interplay between the two words, an example for that. Finally, let's look at some failure cases. In the first example for the teapot, DreamBlend inherits failures when the pre-trained model fails to generate an image with high prompt fidelity. So for example, here, Stable Diffusion fails to generate teapot on top of a pink fabric and instead generates a pink teapot. This is a well-known failure case where internally it has a bag of words kind of representation and fails to associate pink with the fabric and instead associates with the teapot itself. And our method then changes this pink teapot into a teapot that looks more like the input, but there is no way we can add a pink fabric. In the second example, uh, we sometimes fail to perform a successful edit when the subject in this guidance image or the underfit image is very different from our actual subject. So, for example, for a prompt like a stuffed animal in the jungle, uh, the model started with a teddy bear, whereas our stuffed animal looked more like this wolf plushie. And if we start with this image, the DreamBlend has been able to change the color and add a tail here, but it was not able to completely transform this into the wolf plushie. So this is really the motivation for starting with an underfit image as opposed to just stable diffusion to make sure that the subject in the underfit image is closer to what we want in the output. Finally, to conclude, DreamBlend performs a cross-attention guided image synthesis from a later checkpoint guided by an image generated by an earlier checkpoint for the same prompt. DreamBlend combines prompt fidelity and diversity from earlier checkpoints and subject fidelity from later checkpoints during image generation, requiring only inference time adjustment to existing techniques. Finally, DreamBlend enables generation of images with better subject fidelity, prompt fidelity, and diversity on challenging prompts, outperforming state-of-the-art fine-tuning methods. That's it for the talk. And I already see a couple of questions. So, Jimmy, how do we want to do the Q&A?
I can read them out for you. So the first question came in right before you got to your 4 generalization slides. And the question is, does the pattern of high prompt fidelity in the early time steps and high subject fidelity in the later time steps appears in all other text-to-image models?
So this is, I mean, if we look at any of the text-to-image models with this kind of cross-attention mechanism, and also we are focusing on fine-tuning based methods. So those are the two. So if we are fine-tuning it and then this kind, like however you fine tune, like whether you fine tune the model weights or the the text embedding or both. So in all these combinations, we will see the same trend. But of course, if we are not fine tuning and we are using some encoder based method for text to image personalization, then there is no checkpoints and no trend to see. But as long as we are fine tuning a pre-trained text to image model, for this kind of application, we will see a similar trend.
The next question came in from Chris, and it came around the time that you were presenting the effect of the guidance. And the question is, how many images of a subject are needed to fine-tune a diffusion model to get good results?
Right. So usually it's around 4 to 5 images. If you look at the original DreamBooth paper, they have some ablation about how increasing number of images will affect the result. And usually it's like with just one image, it's not the best, and it improves with like two and three and four, and then after that, the gains are not as high. So as when we have like 4 to 5 images, that's pretty good. And also the quality of these images matters. So one of the things we would like is all the images don't have the same background. So that way it's clear which is the subject and which is the background. And there are also, you want diverse images so that you have different poses and so on. That way your outputs can also be more diverse. So quality also matters, but in general, like in most of these benchmarks, you see around 4 to 5 images.
And we'll take two last quick ones. I think they'll be quick. The first one is, have you tried I'm assuming DreamBlend, have you tried it on inputs that show humans? So I guess many of the examples do not include humans. I guess that's the question.
Yes, that's right. We haven't tried this on humans. We basically focused on the DreamBooth benchmark, which has common objects and effects. But yeah, it would be interesting to try it on humans and see how it works.
And the next question, are some models more prone to overfitting than others? I assuming during your testing or experience.
Yeah, so I guess here, like all the common knowledge about this applies. Like the bigger the model, it won't overfit as soon, and it also depends on like your learning rate and all these other parameters, like how quickly it overfits. But in all models, we will see this at some point in the training.
And then we'll take one last question. If there's any commentary that you can offer in regards to resource consumption, specifically around GPUs, to get the research done.
Right. So, as our method is based on fine-tuning methods like DreamBooth and custom diffusion, so it's just an inference time technique. So we don't like do any training as such. Like it's just you take the checkpoints and you do DreamBlend, right? So that way, the only thing that people might point out is that you have to do this twice now, like once for the underfit and once for the overfit. But in practice, when you're using these kind of methods, you anyway have to generate images for multiple checkpoints and do checkpoint selection. So in practice, like these are comparable to one of these fine-tuning methods like DreamBooth and custom diffusion.